Okay, quite often we'd like to represent the motion of an object on a graph. Okay, it just allows us more quickly and more easily to see exactly what that object is doing. And one of the most common types of graphs we use in physics is a speed time graph. Okay, and it just describes how does the object speed change with time. And if you notice, we have some data here that describe that, and we're going to draw a graph on this little image here. So the first thing I do is I draw my axes. So um, just along here, I'm just going to draw a line along this. Now, if you're doing this at home, you do it more carefully with a ruler. I'm just going to try and do it freehand. And we label what's on the axis. So for most graphs, if we're dealing with time, time goes on the x-axis and we put our unit with it. Speed will go on the y-axis here with the unit. So place your quantities on the axis with a unit, and then the next thing we have to do is put our scale on. Now your scale doesn't always have to start from 0. So for instance, if I had numbers that were all in the 200s, there'd be no point starting at 0 because there's no data there between 0 and 200. However, in this case, our time does start at 0. So what I would do is I'd mark the heavier lines on my diagram, and I'd maybe try going up on ones and see if it fits. So if I went 1, 2, 3, 4, 5, 6, 7, 8, that doesn't work. I'd then try 2. So if I go 2, 4, 6, 8, 10, 12, 14, that works. The key thing is that the data should take up more than half your page. And if you notice, this data is going to go up to 10. There's 10 on my graph, and it's more than halfway along the page. So I'm happy. Next one, speed. Biggest number we have to get up to is 35. Once again, mark the heavier lines on your page. Try going up in ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not going to work. 2 will get me as high as 20. That's not going to work. Don't go up in 3s. It gets too complicated to find where the numbers are. So I could go up in 4s and take up more than half the page, but because my data tends to round to multiples of 5, it's probably going to be easier. Start at 0 and go up in 5s. And you can see that gets us as high as 50. We're not going to use it. But the 35, the highest bit of data, is more than half my page. So I'm happy with that. And then all I do is I go and I plot the data. Now, these are nice round numbers. It won't always be the case. These are going to be easy to find in my graph. If I had more complicated numbers, so let's say I had something like the first one was 12.2. That's trickier. What I would always do is, yes, we know that each of these big squares on the y-axis is kind of worth 5. So it goes up in 5 from there to there. I would always work out, well, what's one of the smaller squares worth here? And you can see that there are 1, 2, 3, 4, 5 of them along there. So in fact, each of the smaller squares is worth 1. Won't always be the case, but it makes it nice and easy for us to find where things are in this graph. So my first data is not on the x-axis, the time, and 10. So I just put a little x on that axis, then 2 and 15, 4 and 20, 6 and 25, 8 and 30, and 10 and 35. And then we look at the data and we decide what we do with it. Now, most experiments we're looking for a nice trend line. It's not always the way with objects that are moving. Objects with moving can start, stop, accelerate, decelerate. So we won't always get nice straight lines. We shouldn't expect to. But in this case, we do. So what I would do is I would take a ruler, try and line it up as best I can with those points, and then draw a line. Doesn't always have to go through all the points. It's nice if it does, but we just want a best fit line. Okay, so you'll see the next thing you have to do is go away and draw a graph. Okay, there's data in the folder. Graph paper can be hard to come by. You might be able to get some in your weekly shop in Tesco's. If not, you might be able to print some out from the internet. Worst case scenario, you can just draw a little grid using a ruler at home and use that for your scale. Okay.